Let's solve some problems involving power cycles. Let's solve three separate but all simple power cycle problems. In this first one, the net work of a power cycle is 10,000 kilojoules and the thermal efficiency is 0.4. Determine the heat transfers Q sub H and Q sub C, each in kilojoules. Now this is a system schematic of a power cycle. We have a power cycle that produces work, and it does so by receiving energy from a high temperature reservoir, converting some of that to work and rejecting the remaining energy to a low temperature reservoir. In this particular problem, we're given the work of the cycle is 10,000 kilojoules and that the efficiency is 0.4, where the efficiency is defined as the work divided by the heat input to the cycle from the high temperature reservoir. Efficiency is always defined for a power cycle as what you want, which is the work, divided by what it costs you to get it, which in this case is the energy from the high temperature reservoir. Now what we want to find in this particular problem is Q sub H and Q sub C, the two heat transfers into and out of the power cycle. So let's develop an energy balance for this closed system. And we can see that we've drawn our system boundary around the power cycle itself. And the only thing that crosses this boundary is energy. And so that we can write our closed system energy balance as delta E is Q minus W. But remember, this is a cycle. And for any cycle, delta E is 0. Because in a cycle, you end where you begin. And you cannot accumulate or dissipate energy. So now we have an energy balance of 0 is Q minus W. Well, Q is really the sum of all the heat transfers. We have two heat transfers passing energy across the boundary of this power cycle. We have Q sub H and Q sub C. So Q is really the sum of those. But when we sum them, we've got to consider the directions of the energy transfer. So we see that Q sub H is transferring energy via heat transfer into the power cycle, so QH is positive. On the other hand, Q sub C is transferring energy via heat transfer out of the power cycle. So when we add it to Q sub H, we have to add the negative. So now we've got Q, and this the Q here in this energy balance is actually QH minus QC. So we'll substitute that, and now we have 0 is equal to Q, which is QH minus QC, and then minus W. Rearranging this, we can say that work is equal to QH minus QC. And we can use this energy balance for all power cycles. It's actually, we can derive the same equation when we look at refrigeration cycles and heat pump cycles, and we'll do that in a later lesson. But this W is QH minus QC works for all of these cycles. So let's solve the equation for efficiency. Efficiency is work divided by the heat input. Rearranging, we have the heat input is work divided by the efficiency. Well, the work was given as 10,000 kilojoules and the efficiency is 0.4. So that means the heat input from the high temperature thermal reservoir must be 25,000 kilojoules. Solving for Q sub C, let's rearrange the energy balance and solve for Q sub C. It's Q sub H minus W. Well, Q sub H we just determined was 25,000 kilojoules, and work was given as 10,000 kilojoules. So Q sub C, the work rejected to the low temperature reservoir, is 15,000 kilojoules. Let's look at another power cycle problem. For a power cycle, the energy transfer by heat transfer into the cycle, Q sub H, is 500 megajoules. What is the net work developed in megajoules if the cycle thermal efficiency is 30%? Also, what is the value of Q sub C in megajoules? Well, we have the same schematic for this power cycle. It has not changed from the previous problem. And we can find the work by looking at the efficiency equation. Efficiency is work divided by heat input. Rearranging, we get work is efficiency times the heat input. The efficiency is given as 30%, and the heat input is given as 500 megajoules. Therefore, the work output of this power cycle is 150 megajoules. Now, to find the heat rejected to the cold reservoir, we rearrange our energy balance to give us Q sub C is equal to Q sub H minus W. And Q sub H was given as, or computed, yeah, it was given as 500 megajoules. And we computed the work to be 150 megajoules. So the energy transferred by heat transfer from the power cycle to the low temperature reservoir is 350 megajoules. Our final power cycle problem is given as a power cycle operating as shown with Q sub H is 17 megabtus and Q sub C is 12 megabtus. We want to determine the work output of the cycle and the efficiency. So we're given that Q sub H is 17 million BTUs and Q sub C is 12 million BTUs. Let's find the work and efficiency. For the work, we'll solve the energy balance for work. Well, we solved that previously as work is QH minus QC. We know both of those, so work is just 17 million BTUs minus 12 million BTUs. The work output here is 5 million BTUs. The efficiency is given by the work output divided by the the energy input by heat transfer from the high temperature reservoir. So we have energy as equal to 5 million BTUs divided by the heat input of 17 million BTUs. That is an efficiency of 0.294 or 29.4%.